Number of transistors in a microprocessor or a microchip doubles every 2 years. That's what Moore's law is. While the cost of the computer is halved, and that's what the overall the Moore's law is, and that's what the topic for today's is: AI chip post Moore's law. We all know that Moore's law will more or less stop in around 2025. So how will AI chips evolve after that? This is what we will cover, and we will cover three topics. We'll cover the need for AI chips, we'll cover the state of AI chips market today, and we'll cover the evolution of AI chips post Moore's law, when Moore's law reaches limit. Okay, so let's start with what is the need for AI chips. When we're talking about running artificial intelligence or artificial intelligence workload, the requirements for doing it on the edge is totally different than it's actually running it in the cloud. On the cloud, you have enough compute, you have enough power, so you don't have any restrictions. While if you're running AI on the edge, so let's say a smartphone or even a laptop or on a smart camera or on a security camera, there is limitation on power. So that's one consideration. And there's a difference on what's needed to run AI on the edge versus the cloud. Secondly, you need lots of optimizations, or you can do lots of optimization if you're running AI workloads in the cloud versus on the edge. Even on the edge, you could do that. You will probably do it before you deploy it. And these optimizations will be based on what is actually needed. What are the performance KPIs that's needed? For example, the whole idea about accuracy and performance per watt, these things are much more important when you're talking about edge deployment. A related factor is also the data types used for these algorithms. So int 16 versus float 32 versus int 32. From a simple layman perspective, based on what kind of data or the data sets or the data types you use, the performance that you can expect from AI will vary. If you're using really large numbers, it's common sense that if you multiply these large numbers, it will take much more compute, and hence it will take much more power. And obviously on the edge, you don't have the luxury of having as much power as you want. And lastly, when we are talking about deep learning itself, the need or the requirements for training versus inference is different. And most of the time, we are talking about running inference either on the edge or in the cloud. The requirements for running deep learning inference is different than running for training. Training needs much more compute. And then where do you actually want to run inference will determine to some extent what do you need from the hardware. And all these consideration is what makes up a case for AI chips, where you optimize your hardware and the software on a piece of silicon based on what you need, where you want to do it, what are the performance indicators. Another aspect to look at is what is that deep learning algorithm itself? What is the topology of the neural network? What programming language you're using? How big is that neural network, or how many neurons are there? And all these, when you combine with where should you do the training, where you should do the inference, what are the power footprint, what kind of workloads you may actually expect, how much data will you expect, and where the data lies, all these makes it interesting to try to optimize the overall system. And that's where there's a case for having customized silicon, or silicon that is customized specifically for artificial intelligence workload. And you can use it actually both on the data center or in the cloud, and as well as on the edge. Obviously, the what you need from these will actually differ. Now, our next question is about the state of AI chip market today. So, just following up from our last point about the requirements for AI inference and training, it's because there's a huge difference between inference and training. Training takes much more compute. It's much more complex compared to inference. There are AI chips that are very specific for inference. So Novomind or Intel's NNP are very much meant for inference. Even the older version of Google TPUs were more or less for inference, but now you can use it both for inference and training. NVIDIA's Tigra GPU or Justin TX2 or Cambricon or Sambanova GraphCore, all that are very specifically meant to not just do inference, but it could also do training. Some of the notable AI chips out there includes Novomind, for example, where we have an interesting way to unfold those two-dimensional matrices, where you don't actually have to do that. So these matrices that you use for training are three-dimensional, and most of the time you need to unfold them to two-dimension. With Novomind chip, you don't actually have to do that. Cerberus is another example where they put in a huge number of cores, actually 400,000 cores, on the silicon itself. And that makes it possible to run huge workloads, huge AI workloads on the chip. And because all these 400,000 cores are in one silicon package, it's very easy to do communication between them. So they could achieve a bandwidth of 9 petabytes per second. Mystic is another example, which is a low cost, low area intelligent processor unit. That's what they call it, where they, for these neural network training matrices, they do it in analog. And they claim that because of that, you could do it in a much low cost, low power, and do it very fast. Sambanova is another example that redos the operational hardware to optimize the AI-centric framework. And what they claim is that they can optimize the whole data workflow from algorithm to silicon. There are also autonomous car specific chipsets. So NVIDIA's Xavier chip is a great example, or I would say system on chip is a great example. The Asian counterpart of that is Horizon Robotics, which is a Chinese chip manufacturer that they say they have the brain for the self-driving car. Cambricon is another Chinese chip manufacturer that can do that. Is think about Cambricon also as a AI accelerator, and they say that they are very low power, especially for visual applications. Grok back here in Silicon Valley do inference tasks really very well, and they claim that it's 10x faster than any of the other competition out there. The unique part of Grok is that they, instead of using many different cores, they have one huge core. Remember that we talked about Cerberus, which has 400,000 cores, different cores. Here they have one huge core. GraphCore is another example, which is more or less meant for the data center server market, and they claim that they are much faster than NVIDIA's Ampere A100 GPU. The graph cores processor has close to 1,400 independent processor cores and more than 8,000 separate parallel threads. So they could actually have a huge mesh, and you can put the neural network out there in that. Habana is another example, which was acquired by Intel for $2 billion. That also is a AI accelerator. It to some extent competes with their Nirvana, Intel's Nirvana acquisition. And then there are other companies that are less known. Wake Computing is another one that uses that has a REST-based architecture. Halos is an Israeli AI chip manufacturer. SEMA.ai is another one. What they have, what they call their system is machine learning system on chip. Okay, so that's the current state of art. Now that we know what we have today, the question is what will happen, or how will this AI chip market evolve as we go beyond Moore's law, or as we reach Moore's law limit, which will actually happen in 2025 or so. The answer is twofold. So one is to keep using our existing system on chip, or the typical architecture, and with the modification we now call it is that chiplets, where instead of having all pieces on a system on chip on a one single die, so you have the CPU, you have the HBMs or the RAMs, you have the IOs like the network controller, the Ethernet controller, all that on one single silicon. You have what's called chiplets, where you have processor in one chiplet or one piece of silicon, and then you combine these chiplets into one big silicon or one single die, where now your CPU could have its own chiplet, so you could go out very low in terms of the node, but some of the other aspects you don't actually have to do that. And that's the good thing, where to some extent we could still continue beyond Moore's law, where we go building more and more complex of these SoCs, a system on chips, and here chiplets. The second way to do that is what we call a photonics chip. So instead of using copper or electrons to transfer, or to use to amplify, or to use these transistors, you use light. The two companies that are doing that, there are many more. Light Intelligence is from MIT. They have developed an AI chip which is powered by light. And because powered by light, it's very low energy, and more important, it's really very fast, because it takes some time for electricity to activate a transistor or a logic gate. But when we are talking about light, or when light interferes with light, it's very fast. Light matter is another one. And in both these things, what we're talking about is photonic integrated circuit, or photonic integrated circuits, or ASPIC. And that's what I believe will get us to beyond the Moore's law. So the combination of chiplet and these photonic chips. That's it. That's it for today, folks. I will see you next week. And by the way, we changed our time from in the afternoon to late in the day, so that more of you can actually attend. Thanks, and I will see you next time.